Seeing none, then I'm going to turn it over to my colleague, Will Golay, who's going to tell us about how PyScope controls the telescope. Please, Will.
All right. Hello, everyone. My name is Will Golay. I'm a former Iowa undergraduate. I spent all 4 years of my time at Iowa working on this great instrument, and I've continued it over into my graduate work, where I'm now a first-year grad student at Center for Astrophysics at Harvard and Smithsonian. So today, I want to tell you how exactly do we execute the observations while everyone is asleep. So first, I want to motivate why you might want to roboticize your campus telescope. So obviously, as John mentioned, it's great that we aren't impeding on people's schedules, and we have a lot more flexibility when we don't need a user operating the telescope at all times. Also, I think an underappreciated fact of half-meter and meter-class telescopes is they're much more flexible than some of the major research facilities that are available to us, where proposed time is required, and there's a long waiting period, and scheduling is much less flexible. Whereas with these small meter-class telescopes, there's a lot more flexibility, especially when they're operated as a small group together in the way that we are. And so PyScope aims to enable these things, which is the robotic control software that I'll be talking about and sharing with you. Also, as we'll hear a little bit about in a little bit, having the flexibility also allows us to some unique instrumentation development opportunities that PyScope allows us to execute. So I want to talk a little bit about the history. John already introduced some of this already. The history of robotic telescope development at the University of Iowa has spanned about 25 years at this point, all led by Robert Mittel. The original code was written in C, and it was written by Elwood Downey to operate this telescope that you see in the image here. And this was I believe, a 24-inch telescope, and it was operated on the roof of the Van Allen building at the University of Iowa. However, clearly, a minor city is probably not the best place to put a telescope, especially with scene conditions and light pollution. So this motivated Robert to move the telescope to a better location, and thus came the Weiner Observatory and the motivation to be able to control the telescope robotically and remotely. So there were several iterations of code over several years, and this ended up most recently ending with a Python-based version called the Iowa Observatory Telescope Automation Code, which was written by Kevin Iverson, who's now head of software at PlaneWave, which is the company that sold us the current iteration of our telescope. So as this transition proceeded from Robert Mittel's operation to the operation of the Macro Consortium, this provoked a complete overhaul of the software, as we were interested in using the software not only to control the RLMT, but also to control the telescopes on each of our institution's campuses. So I'm introducing PyScope, which is the software I've been developing to do this. PyScope has 3 main goals. The first one, which I think is what really enables the capabilities of PyScope, is that we are unifying robotic operation under a common and very consistent language set, and it's all Python based. So if you're familiar with AstroPy, it integrates very well with AstroPy. It's designed to integrate with AstroPy, and these things are designed to be familiar to astronomers already and for ease of implementation. The second thing is this doesn't take over manual control. We want to still be able to operate our telescopes in a manual sense, even when we're not operating in robotic mode. And the third thing is we want to be able to support a wide variety of different experiments that users can do. Right now, our PyScope software has been able to support almost every experimental design that we've had come up with student projects, and also it's rapidly configurable, which I'll show in a second here. So here's the package architecture. So there are 3 main modules that most users will be interacting with. The first is the observatory class, or the observatory module. And this is where all of the communication between hardware and software is really set up. So this is where you set up your camera. So if you have an ASCOM camera, for example, this is a very common software that's used to connect to astronomical hardware. You set this up here, which is already built in and supported with the PiScope package. We also support the Maxim DL package and are developing support for other control software such as the SkyX. And then this all gets unified under the observatory class. And the observatory class provides a whole bunch of nice helper functions. For example, you can autofocus. There's an autofocus method with a whole bunch of different options. And another one is a repositioning method where you can point the telescope to a location, it will solve the field, and it'll figure out where the exact coordinates of the center of the image are, and it will automatically bump the telescope the right way to get whatever coordinate you want at the center of your image, which will turn out to be important for one of our other instruments, which we'll be hearing about shortly. The second part is the Telrun part, and this is all software. This is abstracted away from the hardware. So now we are in this location where we have the observatory class we can use, and we know how to talk to this observatory class because we have this nice, common, and consistent set of functions that we know already. So the Telrun class has two main parts that most people will be interacting with. The first one is, I'll mention, is the Telrun operator class. And this is what is actually executing the observations one by one. And then the SchedTel function, which I list here, is what is a helper program to essentially format the observations that you are requesting in a way that the Telrun operator class can understand. And then you hand off the resulting schedule file that SchedTel produces to your Telrun operator, and off it goes, and you can go to bed. The third thing is the reduction package, and this includes some basic data calibration functions and wrappers. And this is to help with and aid in the process of making science products available to students as rapidly as possible. And most of these functions have actually been developed by various students in the macro consortium. And this is another thing we've been trying to emphasize throughout the development of PiScope is student involvement. So here's an example of one of the configuration files, printout of the configuration files. I won't say too much about the details here, but I'll just point out there's some basic information about the site. So we are at the Minor Observatory. We're operating the Robert W. Tell telescope. We are using a Maxim connection to our camera. We have a Maxim connection for our filter reel as well. We also have the calibrator screen, which we'll hear about in James's talk. And we also have our focuser, which is operated through Plane Wave Interface 4 software. And of course, we have our telescope, which is operated with the ASCOM telescope. And we have an autofocus routine as well. So this is an example setup of how one's configuration file might look like. And we're adding new functionality for various other kinds of devices that are not ASCOM devices. We already support all ASCOM devices and Alpaca, but we're looking to add on more things. And this is where we're interested in contributions from the community. We want people to format their drivers in such a way where it can integrate well with PiScope and you can take advantage of all these tools. So PiScope, because we've designed it in a way that is a formatable sort of standard format that you can use for both image naming and directory structure, et cetera, we get this very nice structure that is easy to interface with. And so we have done this, for example, with our observation request form, which you see here on the Macro Consortium website. And this form will automatically populate a schedule file in the correct format and the correct way so that we can add that into our queue and observe it. So these are all things that users can do and integrate into the PiScope environment. So I'll just mention that we are working on documentation and we're working on getting a version 1 release over the summer. And this is a screenshot of our documentation page, and here's the link. And most of our updates will come through here and also through our GitHub page. So feel free to star our GitHub and you'll get any updates that we release. And pretty soon we'll have it available on standard Python indices like pip and Anaconda. And of course, we are interested in the community getting involved. We would like some more information about what drivers people are interested in using for their small observatories. What are we missing? What do we need to add to the package to make it possible so you can use this on your campus observatory? And so we're working on developing all these functionalities and generalizing it. so that anyone can use it. So I'll end there. Thank you very much, and I will ask for questions now.